For the beam and loading shown, A, derive equations for the shear and bending moment curves, and draw the shear and bending moment diagrams. So we would first like to see, apply global equilibrium, and that's going to allow us to know the reaction forces. So let me depict the beam, let's say like this, and we have our distributed load here, just like that. Now, what do we want to do for this? So we have our distributed load here, and we know that up here it's W naught, and the total length of this is L, but all we care about is the reaction force. So we have a fixed support, so we're going to have, let me do it with this, we're going to have we're going to have a By. There's no Bx really, because there's no forces in the x direction. And then we're going to have a moment, which we're going to call MB. So what do we do once we have these? Well, we can say that you got to remember that we can replace W with a load, an equivalent load that is W, that is equal to the area of it. So W naught times the base, which is L divided by 2. And it is at a distance of 2/3 L. So this will be 2/3 L. And this will be 1/3. So L over 3. So now that we have this, what are we going to do? Well, we're going to say that the sum of the forces, where this is positive up, the sum of the forces about the y direction is equal to 0, which means that minus W naught L over 2 plus By equals 0, which tells us that By is equal to W naught L over 2, because it's the only force that's supporting it. And then in terms of the moment, we actually want to do the sum of the moments that are positive counterclockwise around B must be equal to 0. Well, what do we have about B? Well, we have MB plus, or if we use the right rule, plus W naught L over 2 times L over 3. And all of this must be equal to 0. So MB must be equal to minus W naught L squared over 6. And now that we have these two things, we can go ahead and draw our shear and bending moment diagram. So we want to draw it below the beam. So right here. And what are we going to do? Well, the first thing is we're going to make a cut in the middle, say like right here. And we're going to say, hey, this is my X. Here we're going to have V1, M1 at the cut. We're going to have that triangular distribution here. And this is W naught. And then we're going to have our A, which is going to be right here are AY. Actually, sorry, we're not gonna have an AY. My bad. Okay, so that's all we have in there. So we can say that our x, and let me just make a little bit of a separation here. We can just say that our x is going to be going from 0 to L. Our V1 is going to be minus W naught times X over 2. That's my force, right? It is base times height, where the base is X, times height, which is W naught, which is really not W naught, and this is why you need to be careful with this. W naught is at the end, so think about it. Let's think about it real quick. So if we do the sketch, and this is like the trick for this problem, W naught is right here. So here we have an X, here we have L, and so we're trying to find our Y. And we're saying Y over X is equal to W naught over L. So Y is equal to W naught over L times X. And so now we're going to do base, which is X, times height, which is W naught over L times X divided by 2. So what is this going to be? It's going to be W naught over L time over 2L times X squared. And now once we have this, we can do our moment, which is going to be that same shear. So W naught over 2L X squared at a distance of X over 3 times X over 3. So that M1 really becomes W naught X to the third over 6L right here. And M1 is equal to this. Now what are we going to do? Well, now we can plot them. So let's see. If I have this, and this is my V, what am I going to have? Well, I have a quadratic, and we start at 0, and then we increase and increase the shear more and more and more till we reach the very end. So it's gonna look something like this. Nope. It's gonna look like this. Why? Because initially we have a very small area accumulation, and then it gets larger and larger. And so this is how it's gonna look. Now, does that make sense? I'll see, because I lost a minus, but yeah, it's negative. So if the shear is negative, actually, we need to have it under. And so it's gonna start very, very shallow, and then it's gonna go down more and more and more. And then we're gonna do the same thing for our moment. So for our moment, right here, say this is our moment, whatever the units are, and now that is parabolic. Sorry, not parabolic, it's to the third, and it is positive. So we start here, and why would it be positive? Because, so here it's negative, here it's actually negative, and it's negative. And so really it would be negative, so I'd have to extend this line as well. And then once I get to here, I would say that it's going down to a negative value, and then it's going back up, right? It's going back up by an amount that is equal to minus W naught L squared over 6. Now that makes sense. Why? Because if you put L in here, you get minus W naught L squared over 6. So you know that this is a minus W naught L squared over 6, and that this one at the end is minus W naught L over 2. Because as you see, you would put the L in here and it would cancel out with the L at the bottom. So this is what it should look like. And we've derived the equations as well, which are these equations. These equations right here. This one and this one. So this was kind of rough. All right, let's try again for the next one.